This research paper introduces a novel approach to graph anomaly detection, GAD, by leveraging a one-class homophily phenomenon, where normal nodes tend to have strong connections with each other, whereas abnormal nodes exhibit weaker homophily. Existing GAD methods, built on conventional anomaly detection objectives such as data reconstruction or self-supervised learning, ignore this anomaly discriminative property. The authors proposed truncated affinity maximization, TAM, a novel unsupervised anomaly scoring measure that assigns a larger anomaly score to nodes with weaker local affinity to their neighbors. Local affinity is defined as similarity on node attributes or representations, capturing homophily relations within the normal class. However, optimizing on the original graph structure can be biased by non-homophily edges, which can homogenize normal and abnormal node representations. To address this, TAM is optimized on truncated graphs, where non-homophily edges are iteratively removed, resulting in tailored node representations that maximize local affinity. The authors demonstrate the effectiveness of TAM on 10 real-world GAD datasets, outperforming 7 competing models with a significant increase in AUROC, AUPRC. They also introduced 2 novel components, local affinity maximization-based graph neural networks, LAMNet, and normal structure-preserved graph truncation, NSGT, to implement TAM. Figures 1a and 1b illustrate the one-class homophily phenomenon and local affinity distributions of normal and abnormal nodes on 2 popular benchmarks, Blog Catalog and Amazon. The results show that TAMBASED node representations offer well-separable local affinity scores between normal and abnormal nodes, whereas raw node attributes and DGI-based node representations failed to distinguish between them. The paper contributes to the field of GAD by empirically revealing the one-class homophily phenomenon, introducing a novel unsupervised anomaly scoring measure, and proposing TAM, which learns expressive normal representations by maximizing local node affinity on truncated graphs. This paper proposes a novel approach for unsupervised anomaly detection in attributed graphs, leveraging the concept of local node affinity to differentiate between normal and abnormal nodes. The authors introduce a truncated affinity maximization (TAM) framework, which consists of 2 key components: local affinity maximization-based graph neural networks, LAMNet, and normal structure-preserved graph truncation, NSGT. LAMNet is trained using a local affinity maximization objective on an iteratively truncated graph structure yielded by NSGT. This method reinforces the strong affinity among nodes with homophily relations to their neighbors, avoiding potential bias caused by non-homophily edges. The output node affinity in LAMNet is used to define anomaly scores, where weaker local affinity indicates a higher likelihood of being an abnormal node. To enhance the effectiveness of GAD, the authors utilized the randomness in NSGT-BASED graph truncation to build a bagging ensemble of TAM. The proposed framework utilizes the one-class homophily phenomenon, where normal nodes have significantly stronger homophily relations with each other than the abnormal nodes. In unsupervised GAD, the local affinity of each node to its neighbors is used to exploit this one-class homophily property. The local affinity is defined as an averaged similarity to the neighboring nodes, and the anomaly score is opposite to the affinity. This measure provides a new perspective to quantify the normality-abnormality of nodes, enabling a simpler anomaly scoring than existing popular measures. The authors also compare their approach with other GNN-based GAD methods, such as data reconstruction and self-supervised approaches. These methods have shown substantially better detection performance in recent years but often rely on complex reconstruction tasks or auxiliary information. By contrast, the optimization of TAM is directly driven by a new, plausible anomaly measure, which enables end-to-end optimization of an explicitly defined anomaly measure. The research proposes a novel approach for learning anomaly discriminative node representations in graphs. It focuses on maximizing local node affinity to learn tailored node representations for unsupervised GAD. The truncated affinity maximization (TAM) approach is designed to achieve this goal. TAM involves 2 components: local affinity maximization networks, LAMNet, and normal structure-preserved graph truncation, NSGT. LambNet learns a GNN-based mapping function to maximize the affinity of nodes with homophily relations to their neighbors. NSGT removes non-homophily edges by truncating the graph based on the distance between nodes. This process is performed iteratively to progressively remove non-homophily edges and preserve the genuine homophily graph structure. The approach is optimized using an objective function that maximizes local affinity and adds a regularization term to enforce distinguishability of non-local nodes. The optimization is biased by non-homophily edges, which NSGT helps overcome. The approach is demonstrated on various datasets, showing significant improvements in anomaly detection. The paper presents a novel graph anomaly detection (GAD) method called TAM, which leverages the concept of one-class homophily to identify anomalies in graphs. It introduces a new anomaly scoring function that utilizes the local node affinity to detect anomalies effectively. The proposed method uses a two-step approach. First, applying nonlinear spectral graph truncation, NSGT, to mitigate graph convolution biases, and then employing a probabilistic model called LambNet to learn a new node representation space that is not biased by non-homophily edges. An ensemble of TAM models is created to enhance the robustness of anomaly detection. The effectiveness of TAM is demonstrated through experiments on 6 real-world GAD datasets, including BlogCatalog, ACM, Amazon, Facebook, Reddit, and Yelp.Chi. The results show that TAM significantly outperforms 7 competing methods in both AUROC and AUPRC metrics, with maximally 9% OROC and 12% AUPRC improvement over the best competing methods on the challenging dataset Amazon. It also performs consistently well across different datasets, whereas existing methods exhibit varying performance. Furthermore, the paper examines the effectiveness of TAM on detecting structural and contextual anomalies, with results indicating that TAM outperforms all 3 best competing methods in both AUROC and AUPRC on BlogCatalog and ACM datasets. This demonstrates the superiority of TAM in precision and recall rates for both types of anomalies. Additionally, the paper compares the node representation spaces learned by TAM with those learned by DGI and GMI, as well as raw attributes. The results in Table 3 show that the representations learned by TAM significantly outperform all 3 competing representation spaces on all 6 datasets, highlighting the effectiveness of the proposed method in learning a new node representation space that is not biased by non-homophily edges. The paper discusses a novel anomaly discriminative property, one-class homophily, in graph anomaly detection (GAD) datasets. It introduces a truncated affinity maximization (TAM) approach that optimizes an anomaly measure on truncated adjacency matrices. Extensive experiments on 10 real-world GAD datasets demonstrate TAM's superiority over 7 state-of-the-art SOTA detectors. The approach is robust to camouflage attributes and performs well on large-scale graphs. However, it has limitations, such as not handling primarily isolated nodes and requiring large memory for very large graphs. Future work includes adapting the method for datasets with strong heterophily relations and optimizing performance for large-scale graphs. The research paper discusses various graph-based anomaly detection methods, focusing on attributed networks. It begins by acknowledging the contributions of anonymous reviewers and the support from the Singapore Ministry of Education Academic Research Fund Tier 1 grant. The paper then surveys existing methods, highlighting key concepts and methodologies. It emphasizes the importance of graph neural networks in detecting anomalies, citing works such as Oddball and Graph Contrastive Learning for anomaly detection. The authors also discuss the role of heterophily in graph anomaly detection and how it can be addressed. They further explore the use of autoencoders and contrastive learning for anomaly detection. The paper concludes by mentioning the need for further research in this area, particularly in addressing inconsistencies in applying graph neural networks to fraud detection. Throughout the paper, the authors provide detailed explanations of key terms, equations, and algorithms, making it a comprehensive resource for researchers and stakeholders in the field. In the realm of anomaly detection on attributed networks, numerous approaches have been proposed to leverage the power of graph neural networks, GNNs. The literature is replete with studies that employ GNNs for anomaly detection, leveraging their ability to capture complex relationships between nodes in a graph. For instance, the work by 37 presents a comprehensive review on deep learning for anomaly detection, highlighting the role of GNNs in this context. A significant challenge in anomaly detection is the issue of homophily, which refers to the tendency of similar nodes to connect with each other in a network. To address this, researchers have developed various techniques such as the Graph Attention Network, GAT-50, which utilizes attention mechanisms to focus on the most relevant nodes for anomaly detection. Similarly, the Deep Graph Infomax (DGI) model 51 aims to maximize the mutual information between the input graph and its corresponding summary graph, enhancing anomaly detection capabilities. Another key concept in anomaly detection is the use of contrastive learning, where the goal is to learn representations that are close for similar nodes and far for dissimilar ones. This approach has been successfully applied in models like the Graph Neural Network with Heterophily, GNNH66, which can effectively handle both homophilic and heterophilic connections in networks. Moreover, several studies emphasize the importance of considering both node attributes and structural information in anomaly detection. For example, the work by 46 introduces the concept of subtractive aggregation, which aggregates information from neighboring nodes based on their attributes and structural features. This method has shown promising results in identifying anomalies in attributed networks. Fraud detection is another critical application of anomaly detection techniques, particularly in mobile social networks. 57. In this context, researchers have developed specialized models like the Fraud RE58, which is designed to be resistant to both graph inconsistency and class imbalance issues. Finally, there is a growing interest in the development of models that can handle unseen anomalies during training, such as the multi-hypersphere learning (MHL) method. 64. This approach aims to detect anomalies by learning multiple hyperspheres around normal data points, thereby enhancing the model's ability to identify unseen anomalies. Overall, the field of anomaly detection on attributed networks continues to evolve, with a focus on leveraging GNNs, contrastive learning, and specialized techniques for fraud detection and unseen anomaly identification. The authors investigate the one-class homophily phenomenon in graph anomaly detection, where normal nodes tend to connect with each other, and abnormal nodes tend to connect with each other as well. This phenomenon is demonstrated on 8 datasets, including 4 with real anomalies and 4 with injected anomalies. The homophily and heterophily ratios are defined as the proportion of edges connecting nodes with the same and different classes, respectively. The datasets used in the experiments consist of diverse online shopping services, social networks, and citation networks. These include Blog Catalog, ACM, Amazon, Facebook, Reddit, YelpKai, Amazonal, YelpShield, T-Finance, and OGB Protein. The statistical information of these datasets, including the number of nodes, edges, feature dimensions, and anomaly rates, is provided in Table 9. The one-class homophily phenomenon is observed in most datasets, with the exception of YelpKai RUR, which exhibits a weaker homophily pattern. The authors argue that even in cases where the one-class homophily phenomenon is weak, it is still possible to remove non-homophily edges that connect normal and abnormal nodes with a higher probability than homophily edges, resulting in a truncated graph with stronger one-class homophily. The homophily distribution of normal and abnormal nodes is visualized in Figure 5, which shows a significant gap between the two distributions in most datasets. This gap suggests that normal nodes tend to have stronger homophily than abnormal nodes, allowing for the removal of non-homophily edges and the construction of a truncated graph with enhanced one-class homophily. The author's approach leverages this phenomenon to develop an effective graph anomaly detection method. The paper discusses the effectiveness of a novel anomaly detection method, TAM, focusing on its sensitivity to hyperparameters and its time complexity. The results of AUROC and AUPRC are presented for various datasets, showing that TAM generally performs better with increasing ensemble parameter T, which reduces the impact of randomness and truncation. Regarding regularization, adding it improves the model's effectiveness for certain datasets but not others, possibly due to the diversity of attributes. The time complexity analysis reveals that TAM's overall complexity is lower compared to existing methods. The anomaly scoring section demonstrates the benefits of using multi-scale truncation, which improves performance stability across datasets. Additionally, the comparison between shared weights and non-shared weights LAM nets shows that shared weights can enhance performance in certain scenarios. Overall, the paper highlights the advantages of TAM in anomaly detection, particularly in its adaptability to different hyperparameters and its efficient computational complexity. The research paper discusses the performance of the proposed anomaly detection method, TAM, across 6 datasets. It presents AUROC and AUPRC results, comparing TAM with its variants and competing methods. Figures 8 and 9 demonstrate the AUROC results of TAM against Degree and TAMT, as well as its performance with single truncation scale-based anomaly scores. The results show TAM performs consistently better or comparably well to its variants. The ablation study in section C.5 highlights the superiority of the proposed NSGT method over the similarity cut method. Section C.6 includes ROC and precision recall curves for TAM on the 6 datasets. Additionally, the paper provides a comprehensive comparison with existing methods, including iForest, Anomalous, Dominant, HCMA, COLA, SLGAD, and COMGA, highlighting their differences and strengths. The summary focuses on the technical aspects, explaining key terms, methodologies, and the significance of the results, making it suitable for expert researchers and stakeholders. This research paper presents a novel method for anomaly detection in attributed graphs, known as TAM, Truncated Attributed Graph Model. The proposed approach leverages the concept of homophily, which is the tendency of individuals with similar characteristics or attributes to group together. In the context of graph anomaly detection, this means that nodes in a graph are more likely to be connected if they share similar attributes. The authors introduce the concept of non-homophily edges, which are connections between nodes with different attributes. These edges are considered as potential anomalies in the graph. To identify and remove such non-homophily edges, the authors propose a 2-stage algorithm called NSGT, non-homophily edge truncation. The first stage involves calculating the mean distance between all pairs of connected nodes in the graph. This mean distance serves as a threshold for identifying non-homophily edges. In the second stage of NSGT, the algorithm iterates through each node in the graph and samples a random distance value within the range of the mean distance and the maximum distance from the node to its neighbors. If the distance between a node and its neighbor exceeds this sampled value, the edge connecting them is considered non-homophily and is therefore truncated. This process is repeated for all nodes in the graph, resulting in a new graph structure with reduced non-homophily edges. The authors also provide pseudocodes for both stages of the NSGT algorithm, allowing readers to implement the method themselves. Furthermore, they evaluate the performance of TAM on 6 different datasets using various evaluation metrics such as the receiver operating characteristic, ROC, curve and precision recall curve. The results show that TAM outperforms several state-of-the-art methods in terms of detecting anomalies in attributed graphs. The paper concludes by discussing the limitations of the proposed method and suggesting potential future directions for improvement. One limitation is that the current implementation of TAM assumes that the attributes of nodes are numerical, which may not be the case in all real-world scenarios. Additionally, the authors note that incorporating additional information about the network structure could further enhance the accuracy of anomaly detection. Overall, this paper contributes to the field of graph anomaly detection by introducing a new perspective based on homophily and non-homophily edges. The proposed TAM method demonstrates promising results in identifying anomalies in attributed graphs and provides a foundation for further research in this area. The research paper presents a novel anomaly detection method, Algorithm 2 TAM, which leverages graph neural networks, GNNs, to compute anomaly scores for all nodes in a graph. Given a graph G equals V, E, X, the algorithm first computes the Euclidean distance between connected node pairs. It then initializes a GNN and truncates the graph at multiple depths, updating the graph structure. Subsequently, it applies LAM-NET, a layer-wise anomaly detection approach, to each truncated graph. The anomaly scores are calculated using equation 2 and aggregated over multiple sets of graph truncation depths. The optimization process involves minimizing a loss function that includes both the anomaly scores and a regularization term to encourage diverse anomaly scores across nodes. The parameters are updated using stochastic gradient descent. This method offers a multi-scale approach to anomaly detection, enhancing its robustness and accuracy.